一会儿来。你这么，其实这种思想去吧。手动路没有自动路的亲戚。
这个已经过三了，那应该是那个自动路，应该这个自动路。
不要钱。这个应该是自动录的吧？
你要录的话，必须得用
手动，
必须得用这个电脑呀。
那学校那个系统有没有录课的？
学校好像你得点那个，你
是课程录，是不是有什么课程录制？
对。
但是那个东西能不放下来吗？就这个能不放，只开电脑不放。
不要紧，我知道了，没事。行了。
你知道了？
学校系统应该都有。因为我们是在调课，
要不那个你必须用四块黑板。
四块黑板好。
啊，这样能录吗？我也不太懂啊。啊，那行。
开电脑一定会把这个降下来。
直接放了。对，我们12月9号的课调到了今天。标业玉12月9号要出差，我要去这个剑桥大学。12月9号我们就换成习题课，所以12月9号的课我们调的。我们顺序不会调，我们今天还是接着上一次的讲。上课了。So let's continue. So in the end of last lecture, we discussed the path integral. So the picture to derive the path integral formulation of quantum mechanics is very, very simple. As we saw last time, this is my time direction. Yeah, we will say why I choose the time direction to the left. Okay, because I want to connect the path integral to the amplitude, to the transition amplitude. Okay, and then transition amplitude we evolve the state using Hamiltonian is from the right state to the left state. Okay, that's the reason. So if I start from a time Ti and start from some position, see here, xi, I want to calculate the transition amplitude from this xi to some Tf, which is my final time, and some other position xf. Okay? So this is a very, very classic. This is a very concrete quantum mechanics problem. Okay. Then we need to calculate this transition amplitude from I to f. And before we learn the path integral, the way to calculate this transition amplitude is just using my Hamiltonian. Using my Hamiltonian to evolve. Okay. For example, if my Hamiltonian is time independent, then the only thing I need to calculate is this one. Okay? And from a position eigenstate and start to evolve this state using my Hamiltonian and then take an overlap of my final state. Yeah, that's it. But in general, H does not need to be time independent. For example, H can be time dependent. Okay, time dependent. Then what do I do? So what I can do is just slicing all this time, the time interval into many pieces. Okay. Okay, and then for this small interval, this delta t, then I can use this kind of evolution because h is approximately constant. Okay, for that small interval. Then I can just take product over this small piece. Now, furthermore, what we can do is that we can try to calculate this amplitude in some alternative way. Okay, alternative way. What we can do is we can insert for each dashed line. Okay, for each dashed line, we can insert a complete set of X state. Complete set of X state. So for example, like I go from here, this is the X1. This is this is the T1, for example, and then this is the Tn. Then this becomes n+1 interval. Okay, or if you take this as a Tn minus 1, then this is the n intervals. Okay. Then what we can get is if I insert a complete set of X state for each dashed line. This is what you get, okay? And then finally the xi. This is what you get, okay? Now the point is, one can compute this block, So we use this entire thing as many blocks. For example, such a block, and here x1 with this xi, xi is the initial, and xn here with the xn minus 1. Okay, that kind of block. So in general, the block is xj plus 1. In the middle is minus I h delta t xj. Okay, so this block when we compute this, So this is nothing but how to compute this one. So we insert once more another p, complete set of p set. Why I want to do this? Because I want to write this Hamiltonian explicit. Okay, this Hamiltonian is defined as m squared over 2m plus the potential. Okay, so then I will have minus I p as operator squared over 2m plus v, and we know also v is the function of x. Okay. As an operator, so this is x. So now because this h is inserted. This is inserted in the j's block. In the j's block. So here x j hat tj. Okay. tj. Because in general the potential could be time dependent. Right? In this case it's okay. Because I just focus on the block, the j's block. Okay. In the j's block, I pick up the potential v, so v should be the vx hat tj. Okay. So this is my potential, and I have to compute this. Insert t. Now over this xj. Okay, this is what I need to compute. Now I treat this piece hat square act on the left, and this x hat acts on the right. Okay, they all becomes numbers because this is an eigenstate. So what I get is this e to the minus I v j tj delta hat delta t e integral e minus I e squared over 2m. Now I have something like this x over p. Now all this becomes the number to pass through this state. Now I will have a p overlap with another xj. But we do know this overlap, x overlap with the p. We know this is nothing but e to the IPX. Okay. Yeah, so this is what I get. Now you simply realize this is the Gaussian integral. You can calculate it explicitly. Okay. So you finish this p integral. You can complete this p integral. Eventually, you get that block. Eventually, that block gets equals to some prefactor coming from this Gaussian integral. Okay. Times e to the minus I v delta t with e I m over 2 delta t squared xj plus 1 minus xj squared. Okay? Now this part, you realize that this is nothing but the mv squared over 2 minus potential, okay, which is the Lagrange, and there's a common delta t. There's a common delta t. So go further. This block will be equals to a prefactor times e to the I Lagrange times delta t. Okay? Times delta t. Now this is only a block. There's an integral, right? So you take the many blocks, take the product, put them together. Okay, put them together is equally to say I do the integral over t, right? Because this is delta t. You sum over all this small delta t, meaning you do integral. And in general, L is a function of t. Okay, so you do the integral over t, over time direction. Okay, you do integral over time direction. But there's a little subtlety here. So to understand after this integral over t, to understand the L as a so then you basically get action, right? You get action. So that action is for what? That action is for a particular path. Okay. For example, you assume this x as a function of t is a smooth function. Okay. The smooth function. Then it's this action is defined for a particular path. Now you take the integral over all this x. Okay. All this x. Trying to say is if you just before you take the integral over all this x, you just get some action. You just get some action for some particular path. Okay. For some particular path. Now you take the integral over all these x. Then it's equivalent to say you just sum over all the paths. For each path, you address it by the action. So eventually, the total amplitude will be the same. This is it depends on how many pieces you cut into. If this is n piece, then this is n to the n prefactor. Because this one, this is L x n dot. There's t dot e to the I L x1 dot delta t. Okay? So you get many pieces and you put them together. But you shouldn't forget these boundary conditions, which is very important. Okay? Okay? All this cutting procedure, all these different paths, they have to respect the boundary condition. Okay? That's the given data. Okay? It's given data. So now you take the continuum limit, which is delta t goes to 0. And you get this total amplitude is equal to up to a prefactor. You sum over all the paths, okay? Let's use the capital D. Let's use capital D. Distinguish from the small little d. Little d means the usual integral, okay? Here I use capital D. And this is the integral. This integral measure is for the path, okay? This is different from the previous integral. Okay, this capital D xt. Sometimes we also write in this way. Okay, this means that a sum over this integral means a sum over all the different paths. Okay, all the different paths. One path is specified by xt, right? Right? Because xt describes a function, okay, which describes one particular path, not a sum over all the paths. So for this reason, we call it this is a path integral. It's very intuitive name. Okay. Now x here is action here. The weight factor here. The exponential I times the action, and action is also a function of xt. Right? If you have some problem to understand this kind of formula, you should always discretize this to understand it in terms of sums. Okay? You can just discretize this integral, then it becomes sums. Okay? We know all the integral must be some sum. Okay? This is a little complicated sum. Okay? But it's a sum. It's not a big deal. It's a sum. It's a sum. And if you tell me all these paths and in particular all the weight factor, this weight factor or the action for that path, then I can put this together to sum them together, get a result. Okay. So this is the meaning of path integral. But this is only for quantum mechanics. We want to push this idea to the field theory. Okay. We want to push this. Yeah, we are not satisfied only by this. Push this. So how to do it? It sounds a very challenging problem, right? So even in quantum mechanics, it's a little complicated things. For example, if you try to sit down and try to calculate this result out of this path integral, it takes little time, right? It's not a simple integral, right? To really do something, I mean, this is a complicated sum. Okay? It's a sum. But once you push this to the field theory, then the first thing I think is the most important thing I have to remind you is the table we drew in the first lecture. Okay, because now we want to extend this framework from quantum mechanics to the quantum field theory. So you have to be very, very clear about the analogy between quantum mechanics and quantum field theory. From the very, very beginning, we already mentioned, to make the analogy very clear, you should understand, for example, in quantum mechanics, the position eigenstate we usually denote by the x state, and x itself is an operator. Then you act as the eigenstate regarding the eigenvalue, which is x as a number. Okay, as a number, right? Then this is what I have. Okay, this is what I have. Now the analogy in quantum field theory, now the x has to be promoted to the phi field. Okay. Now in field theory, x is no more an operator, but phi isn't. And x is an index to denote phi. Okay. Let me still put in this equation. Then what you should be clear is this one. Okay. Then the eigenvalue now is a function. Eigenvalue is a function. Phi itself is an operator. Eigenvalue is a function. And the configuration eigenstate now we denote as this phi state. Okay. This is the analogy in quantum mechanics for this x. And also for momentum. For momentum, for example, if you put in quantum mechanics in this way, okay, P operator acting on this P eigenstate, you get again you get a number, right? P or vector number as the eigenvalue. Now in field theory, what you should put here is you have the conjugate momentum. And the conjugate momentum eigenstate will be pi. Now by acting by this operator, you get the eigenvalue pi as a function. Okay. This is what you have. Okay. And similarly, this is the that we used here. In some step, we have to compute this x overlap with p. Okay. See, it's x eigenstate overlap with p. So in quantum mechanics, this is e to the minus I p dot x. Okay. This is in quantum mechanics. Now you have to make the analogy in field theory. So what is that? It should be the pi overlap with the phi. Okay. Okay. Then what you get is, because these are conjugate variables in field theory, what you get is e to the minus I integral. These are the functions. You have to put the integral in order to get some number. Okay. So this is the why I write this or make this table, because we want to make it very clear. In order to find the analogy in field theory, what are the complete set of this eigenstate in field theory? Okay. Then it should be a phi or pi. Okay. Phi or pi. Right. This is just a complete set of the split. Now with this in mind, the last one. So what should we compute? That's the question. So here in quantum mechanics, what we compute is this one, right? Is this one. What is this? This is the overlap. The overlap between the xi, ti with the xf and the tf. Okay, this is the overlap we compute in quantum mechanics, right? Right. So why I write this way? Because this is the Schrödinger. This is the Schrödinger picture, which is equal to what I put there. Okay. Okay. That's the Heisenberg, because this operator takes the evolution, took the job to evolve. Okay. Now if you put this is the same thing. Okay. You can write it this way. Now what you should compute in field theory is, for example, you can compute some vacuum state. Overlap with vacuum. One is located at initial time Ti, and another is located at final time Ti. Okay. Because you want to find some state, right? The game is to evolve some initial state to some final state. Okay. So what is the simplest choice in field theory? So we already talked about a lot from the canonical quantization in field theory. Right? Simplest state will be the vacuum. Okay. So I can choose the vacuum state at the, for example, the past infinity. Okay, to the future infinity, for example. So it will be the simplest choice. So yeah. So we can choose it in this way. We can choose it in this way. And then all other things will be very straightforward, right? You see? It will be just straightforward. You can push. Okay. For example, you can just following this procedure. You start from some vacuum. You evolve it by using the Hamiltonian, because we know all this canonical Hamiltonian formulation for field theory, right? We know all this phi eigenstate and pi eigenstate. Okay. So just make this extension straightforward. Okay. So let me write a little bit more steps. So let's do it. So again, first let's specify the Hamiltonian. Specify this Hamiltonian. So Hamiltonian will be the half analogy to that p squared. This will be the pi squared plus some v as a function of the phi hat. Phi hat. Okay. This is maybe my first series Hamiltonian. Okay. And this will be my first series Hamiltonian. In general, it could be time dependent again. And then what you do is just forwardly this overlap with this will be again. You just promote this picture to the field series setting. Okay. You think about it from some initial state to evolve, and then take over the final state. You first. Now in field theory, the variable of course will be changes, right? It's that x is now it's not x but phi. Okay. Now where is the x? In field theory, we already understood. So x becomes some index of these degrees of freedom. You can think about it. There are some spin degrees of freedom. Spin aligned along some special direction with many indexes. Okay, with many indexes. That index is the x. Okay? Located at different positions. Okay, and at each point, this spin can take some value. Okay. Then it's in the continued limit. This is just the discrete time field series. But you need a bit of imagination. Now, anyway, but in terms of formulas, picture-wise, it's a little bit complicated. But algebraically, it's really straightforward. Okay? Just replace everywhere the p, the x by the phi, and the p by the pi. That's it. Okay. Algebraically, it's very straightforward. Okay. So what I get it will be the instead of that dx, instead of this dx 1 dxn, what I get will be the d phi 1 d pi n. Okay. So this kind of integral again means the sum over all their configurations. Okay. This is a complicated space, but this will be the element of x complete set of x state or p state. So first, let's write it this way. Then the remaining part is straightforward, right? It's just like a vacuum, and this is the splitted time interval. Again, I split time interval. I guess this is h hat located in plus Tn, and we get the phi n and phi n. Okay. So this index 1 to n is only labeled at which time interval you are located. Okay. Because we have many. We have n piece, or n plus 1 piece. So we have n independent complete set of the phi state. Okay, of the phi state. That's why we need to. Okay. So last term will be the phi 1. And times e to the minus I third t h hat. So this is t n. So this will be the t0. act on the ground state. Okay, that's it. It's not complicated. Okay, the same thing. Now you just decompose this whole amplitude, which is from vacuum to vacuum. Okay, from vacuum to vacuum. It covers the time interval from Ti to Tf. You just split again. You just decompose this time into many more time pieces. Okay. Then for each piece, you insert a complete set of 5 states again. Okay. Because 5 states is the analog in quantum mechanics, the X state. Okay. And the same thing. Okay, the same thing. So now the job is how to compute this one, right? Again, you use the very similar to this one. You see, this formula is the same as that formula, right? This is in quantum mechanics, that's in field theory. Okay? The same thing. Now, how to compute in field theory this block, each block, okay? Meaning that the question now is how can I compute this 5j plus 1 e minus I third t h hat tj act on the 5j. Okay? This will be the analog to ask this question, right? See? Really the same. Okay. Now I ask the question here. So how to compute this one? Just follow the procedure here. Right? Just replace all the p state by pi. That's it. Same thing. So yeah. So you insert all this pi. Once more, you insert this complete set of the pi state. Then what you get is pi j, and e to the minus I third t, and h, right? And h. Act on this 5j. Okay. Then, as what we did here, you write h explicitly in terms of pi square plus v. Okay. Okay. Then everything will be the same. So you act both left piece to the left and to the right. Then this Hamiltonian operator passes through the state. You get numbers. Okay. Because this is the eigenstate. So eventually you came up with some pi integral. Okay, like this. Some pi integral. That pi integral is a Gaussian integral. You know how to do it. You perform this Gaussian integral. Eventually, you are done. Okay? Okay, so after a few steps, or maybe you have to write more. So this is the E, I, J, E to I, E, I, J, 5, J plus 1 minus 5J times E minus I third T. Integral half I j squared plus v by j. Okay. This is what you get. Now you do the Gaussian integral. You perform this integral. You do this Gaussian integral. You do this Gaussian integral. Then you get again a prefactor times e to the minus I delta t. You get a Lagrange basically for phi j partial t phi j. Okay, previously you have a velocity. Now we have this partial T by J. Okay? You get the Lagrangian. That's the answer. Okay. This is the answer. This is the answer. This is the answer. Now you put all this block. This is only one block. Okay. You put all the block together. You put all the block together. Eventually, the overlap will become some prefactor up to some prefactor. The integral now is a path integral over this field phi. Okay. And with the weight factor, if you put all the pieces together, one piece for one piece of time interval, you have Lagrangian. You take the time integral, then you get action. Okay. So you get this one, okay? This is the final answer. Well, it looks simple, right? It looks a simple integral, but it's actually not simple. Okay? As you see, in order to derive this, we spend a lot of time, right? To derive this one, right? So it's not simple in the sense this is really a path integral over phi, okay? Okay? So picture-wise, you can make an analog. You can make an analog of the picture, okay? It's hard to make it visible, but you can imagine, okay? So this path integral really means that all the configuration, you have to sum over all the field configurations, okay? All the field configurations. Each field configuration will be analog to this function xt for this each path here. So in field theory, the path really means different field configurations. So in quantum mechanics, the path is really the path, okay? So this looks the path in the real world, but in field theory, it's not, okay? Okay. So again, this sum is for all the field configurations, all the field configurations. Okay. Right. Yeah. Well, okay. Good. What I'm trying to say is, if you really want some picture, maybe you can make it this way. This is my final time. This is my initial time. Okay. Now let's try to lattice my field theory. Okay. Let's try to lattice my field theory. Then the field configuration will become some waves here. Okay. Some waves here. Yeah, some waves here. So point is you have to sum over all the possible waves. Okay. All the possible waves. Okay. Schematically, this is my phi. This is my phi direction. Okay. You really sum over all these configuration waves. Okay. In this space-time region. This is my time direction. Okay. This is possibly my x, my space direction. What you should sum is really the configuration. Okay. You don't sum over x, but you sum over all the possible configurations. Okay. Imagine there are many spins. The field theory is nothing but there are many spins located in this lattice. Okay. Okay. There are many spins located on this lattice. Okay. For each lattice, the spins can take some value. Okay. Now you can imagine. For that purpose, you can imagine that the wheel is essentially characterized by configuration. Okay, it's phi configuration. So this is a 1+1 space-time field theory picture, if you want. Okay. So So you sum over all these configurations. Okay, all these main configurations. That gives you this field theory path integral, right? So it's really complicated thing. But conceptually, I would say this is quite clean because we know the weight factor precisely. So for each configuration, you just evaluate the action. Okay, then you put it into this phase e to the is. Then you sum them together. Okay, so conceptually it's very clear. It seems the remaining problem becomes technical calculation problem. Okay, conceptually it's very clear. Right? Now maybe the only, again, technically, maybe this phase factor is another challenging problem, okay? It's not look, this potential is not something real, okay? It's really a phase, so, okay? So it's challenging to sum a very complicated phase together, okay? Because in phase, it can easily happen, the cancellations happens, right? It's not some trivial number sum. Okay, it's a phase. But so far we're talking about the Lorentz field theory, as you can see, because from the derivation we do the time slicing. Okay, we do this time slicing. And in statistical mechanics, in statistical mechanics, actually. What people quite often do is, without this I, okay, put a minus, okay, some e to the minus. And in order to specify this, they emphasize this some Euclidean action, okay, Euclidean action. So they do different things. In that case, maybe easier, okay, because there's no I, it's not a phase, okay, it's really a number. Okay? Everything is a number, it's real. So just do that sum. But in this case, it's a phase, because this is Lorentz. This is not Euclidean. We have physical time, so this is Lorentz field theory. Okay, so a few remarks. So to understand this, because this is our first time to meet this kind of path integral in field theory. Let's go slowly to understand what it means. Okay. So the path integral really means the sum over all the field configurations as emphasized. Okay. All the field configurations. Now we know we can restore the H bar, okay? Because H bar has a dimension of action, right? Right? H bar has a dimension of action, right? We can recover H bar without just taking the natural unit. We can recover H bar. So if you recover H bar, then this formula becomes here, then there is a H bar here, okay? There's a H bar. So IS over H bar. Okay. You recover H bar. H bar should appear here. Then you take if you take H bar goes to zero limit, this will be the classic limit. Okay. Classic limit. Why? Because H bar goes to zero limit, we can use set point, right? See? Because this is the integral, right? This is the integral. If H bar goes to zero, we can use set point. Set point approximation, okay? Set point approximation. Like there. This is the integral, right? What is the set? This is the set point approximation. It is a very, very general trick. You can even do for the ordinary integral, right? In your integral calculation, right? Calculation. So when H bar goes to zero, when you do the set point approximation, you realize that, okay, the dominant configuration it picks up is nothing but that one satisfy equation motion, right? because this is delta S, delta phi equals to 0, okay? Right? So this is the classic limit, meaning that the equation of motion dominant, the integral is dominant. By equation of motion, right? Is dominant by that, by those, this phi, equation of motion, okay, or classic solutions. Okay. Now we come to the key question. Before that, so do you have any question about this formulation? Okay. So I suggest it's an interesting exercise. I suggest you to do every step carefully to see the magic. Okay. But this is really a straightforward extension from the quantum mechanics, right? And it's beautiful. Yeah, maybe one more comment is now this formula, if you look at this carefully, it's a little magic because left hand side we have some state. Okay. So we define the field theory state in the beginning of this course very carefully. Okay. By using this this AA dagger build up this Hilbert space, we know what are the states in field theory. But somehow from the right, there's no state, right? So what happened? Okay. So right hand side, all the other functions. Okay. There's no piece correspond to some operator or state. Okay. It's just the ordinary functions, right? Because the definition itself in the path integral don't need any state or operators. That's it. Okay. Right? For example, if you're not sure, then you can always go to the statistics physics. Okay. There is everything is really clear. You can even put the path integral on the computer. Okay. It's just sum all the spin configurations. That's it. That's what they need. So you really can produce some number. You don't need to make this fancy conception like an operator or state or whatever. You don't need that. You don't need. So the something hidden here is really the boundary conditions. Okay, is the boundary conditions. Okay, that's what you should keep in mind. So quite often or always in path integral, if you want to figure out where are the state, okay. You have to go to boundary conditions, okay? Okay? You see? This, yeah. The last thing is whenever you have confusion in field theory, you have to go back to the quantum mechanics. Right? Unfortunately, I use the quantum mechanics. So in quantum mechanics, right? In quantum mechanics, look, in quantum mechanics, we specify the boundary conditions, okay? Boundary conditions here. From the xi to xf, right? That's my boundary condition in the path integral. Okay. Precisely that boundary condition corresponding to the state. Okay. You see? So each boundary condition corresponding to the state, okay, xi. Okay. That's the point. Now we ask the very, very important question. So far, so good. Okay. It seems we derived in field theory the path integral formulation, which can tell me how to calculate this transition amplitude. Looks good. We want to ask more. For example, since you already tell me this kind of formulation, before you limit it as a path integral, then I can ask, what is the meaning of something like this? The path integral with some insertions, okay? What is the meaning of a path integral? For example, I use I, some integral, some path integral. Now I skip this xt coordinate, but you should keep in mind that it should be there. Okay, you can ask this question, right? Because now it seems you know the physical meaning of the right-hand side, the path integral, right? Then nobody forbid me to extend this structure to a more complicated level. Okay, so I can try to do the path integral with some insertions. Do some insertions. No? Insertion means I have additional field here in the integral. Okay? When you do this sum, not only for this piece, but I have another 5 field here. Okay. 再插入一个场 okay? That's perfectly well defined, right? Does not give you additional complication, right? If you know how to deal with this part, you should know how to deal with this part, no? Now, how to answer this question is very, very challenging. Okay, this is my first day to meet this path integral. How should I deal with this question? So, the idea is always go back to this Hamiltonian picture. Okay? Always go back. That's the idea. If you don't know how to answer this question, what's the meaning of this object, then you should go back to this. Go back to this picture, right? Because we know this picture is equal to is the Hamiltonian canonical formulation of the path integral. Okay. Then if it happens, I know how from this picture how to create something like this. Okay. That's the job, to create a factor phi or field insertion phi inside this path integral. Then I know the answer. Because this is my ordinary language. Okay, it seems I'm sure I know the precise meaning of this kind of language. Okay, and this is my new formulation. Okay, if you ask a new question in this new formulation, I can go back to the ordinary formulation. Okay. And then I can try to answer this question. Okay. So for that reason, so let's put a more index, say j. Sometimes we can do also j here. It's not much meaning for this j, but we can do it here in order to denote. And in order to denote, this is at the j's time interval, right? Okay. So what I'm trying to say now is, in order to go back to this slicing picture, okay, I can always fit this insertion phi into some time intervals, right? Right? For some time intervals, then I can try to go back. So J knows the J's delta t when we slice the time. right? Then you have to tell me what is T, right? Or what is Tj, okay? If I know what is T, then I know what is Tj, okay? Right? Because J is just to specify when you discretize time. So this is the new question after we slice the time. Then what should I do? As suggest we can go back to the Hamiltonian. Derivation of the path integral. Okay, which is here. Now I ask to this formula, right? Because this is the same of that path integral. Now, you with some additional insertion phi, then I ask a question here. Can you tell me which operator does the job? Okay. From here. Which operator does the job? Does the job of what? Does the job to give that factor, okay? Give that factor here. Then the answer becomes immediately clear. Immediately the answer becomes clear. What you need to do is just you act a phi operator. You act a phi hat operator precisely at the time Tj, okay? That's it. Right? Somewhere here, dot dot dot. Somewhere I have this phi j, right? Phi j. Okay? You see? As we make it somewhere in the beginning of the table, okay? If you act a phi j hat operator, okay? And this eigenstate phi j, then you'll get a function phi j, right? Because this is the eigenstate. If you act an operator on that state, then you get this function, okay? You get this function. So let me write this. Because this is important. I write this. Read this. What I mean is, if you pick up this by J's time block, for example, this one, E minus I. If you pick up this block, okay, so this is the J's block. Right? Okay, if you pick up this one, if you want to get additional phi j x j factor, then what you should do is you should act phi hat on this block. That's it. Okay. Right? That's it. Okay. So this operator does the job. This operator does the job. Operator. Now Now, if you formulate in this state, everywhere you see state and operator formulation, and you also know this phi hat operator does the job, then really I can build up this equation. So up to prefactor, this path integral. Okay, this path integral with some insertion is equal to 1-point function of phi hat. You see? Is it clear? This is what I can get, right? What I can get, okay? What I can get. Then maybe this equation is a very simple equation, but maybe first impression is it's a little magic. Why this complicated thing becomes a very, very simple 1-point function. We know this before, right? Very well, right? We know this before. But y equals to this one, okay? And this is the derivation. The idea is try to translate this path integral back to this Hamiltonian description. And then ask which operator act on that Hamiltonian expression can give this factor. Okay? Then you realize that it's nothing but phi hat located at some in this corresponding space and time, t, xj, tj. Okay? If that operator does the job. Well, you can check. You can check. This is correct, right? It's correct. It's not something cheating. For example, if you turn off this phi, if you set this phi is, for example, identity, right? Or you turn off this phi, then this becomes the identity operator is 1, right? The identity operator. Then you get some purely some vacuum state overlap with some vacuum state, right? Right? And we know that's equals to this bare path integral, right? Up to a prefactor, okay? Right? The point is, by using this kind of vacuum, we always mean a vacuum from the past infinity overlap with the vacuum at the future infinity, okay? Okay? This is the past infinity vacuum, evolve by the Hamiltonian, and then finally overlap with this future vacuum. Okay? Okay, so it's not a non-trivial. Okay, you can normalize it to be 1, but it's not non-trivial. Physically, it's a non-trivial process. So he identified with this path integral. That's what we showed. That's what we showed. Where is my? Yeah, that's what we showed here. What we want to show here. Okay, look. So sometimes we hide this time, okay? If we don't, sometimes we just hide this time. For example, if we hide this, usually we mean this, okay? Okay, this minus infinity and plus infinity specify the time. Specify the time. Okay? This is what we really mean, okay? Okay? Now we have some additional operator insertions, meaning if you evolve your vacuum, if you up to this Tj point, right? Tj is some particular time, right? Now then you meet an operator, right? Right? Then that state have to be acted by this phi hat, okay? Once, and then continue evolve, okay? That's what the meaning of the right hand side. So in the left-hand side, it's nothing but I just put additional field insertion, okay, inside this path integral, and then evaluate. These two guys have to be equal. They are equal. OK， 我们休息一下，再继续。
我就一直不知道它这个节点是怎么推过去。
啊，这是 set point， 做 set point 啊，你在做共享积分的时候也可以做 set point。set point right。
h 趋于零的话，你这个它在偏零德尔塔 s 等于零的情况下，这个会正当的无穷宽，
哦，正当无穷
的
宽
cancel 掉。
但我就是为什么我就是不理解为什么正当无穷宽会 cancel 掉？这件事情并没有人认为。
另外一个方法，也就是做个 analytic continuation， 还有 Euclidean， 也有个4point，这个方法和这个积分，这个就是通常的积分，没有任何 fancy。right， 通常的积分也是有 set point，set point 近似，原因是什么？你前面有一个无穷大的 factor， 前面有个无穷大的 factor， 你只有在德尔塔 s 等于零的时候，是 dominant，
对，
所有的其他的都是 subleading。OK， 所以这个刚好是经典解的处理地方。
是，这里实际上我用，我如果用薛定谔表现，那我不是这里要再插一个这个，要再插一个这个，但是我们这里上面推哦，
本来图
哦，
我们还没图，我这个得对，
好，就是要这里要，
是的。
我提到挺少，我觉得这种肯定是直接定型为这样的话，我估计用之前的资料就多少东西。
还有什么？还有什么 ？exchange between 这两个 picture。
这只一个，我要
这个和之前就是在复回的特定就把这个当成是那种位置的一个模来的，这个是不是跟之前不一样？就是你应该是说把所有的这些那个 e 的 i h 的那些所有的那个例子，然后体现这个位取一个体现这个。
你再说一遍，后面我没听明白。e 的 i h 是什么？
就是前面那些，e 的这个东西的特征是，就
特征值。
是应该是那个。
你问题是什么？再说一遍。
就是之前不是还写了一个那个画了一个表
，right，
那个东西是你写成 file， 所以这个啥不用。
No， 是一样一个 file，
一个 file。
right。啊，为什么？因为这就是可以场构型。
但是这个有的问题，就是你想，这个它组成一组框是一个 basic，
yes，
所以它应该是合数的。然后这样的话，你取一个极限会出现这个东西不够了。
哪一个极限？
就是你上这边肯定是要对这个 slice 取的越来越细。
No， 这是 totally different 的极限，这跟这个构型没有关系。那个极限是只是它，刚好这个。我这唯一取了一个极限，就是德尔塔 t，which is here， 德尔塔 t 取连续时间极限。 他们附近的就是周末回家呀，你不也是附近的？
啊，我是浙江的，我又不是上海。我回不，不过我下周去。周末回家，高铁这也是挺好的。
我花在地铁上的时间要比高铁长。
啊，对，地铁要1个多小时，高铁45分钟。
要不要收费的时候要收费。
你找怎么上海的？
要看买到哪里的票，大部分只能买到虹桥、上海站的票价最强。
这个东西，它不是这个，这个硬的东西。
这里的东西，它这种仪器，这是我这个父母的这个，然后你这里你要apply 东西，这个实际上表是这样的。说这两个东西是 slide 出来，这里是有个说明，就是这里的这个
画画后面应该是这里有个那个我的问题是，然后会打出来，这个你想说这个东西的哈密跟那个 EXPIH 有那个 community， 然后这个东西。应该等这个难的问题。你看这等式两边能等起来了，这是个规的，这是个数，这是说规的。但是之前不就是这个？这个是对的，不是，因为它是在中间插的。它这个，因为你在这里面插的话，你这里一个画，这里有个发一针，你这个东西一直都含着你这个不能把它拧到这里，因为你后面这里面就是是这样的底。
Okay.
这个得插在里面，就是吧。
Let's continue. So we understood the one-point function in terms of Hasidic universe. Now the natural question is what about the two-point function? Okay, what about two-point function? So as you can see, we are just to translate everything. We want to translate everything we understood in the canonical quantization. Now in this new picture, in this new framework, Hasidic integral. The next question is about what about the two-point function? Meaning that if I have two insertions, what's going on? Right? Nobody forbid you to put a two insertion here, right? For example, one is x1, p1. Another, put the same field but located at the two different space-time points. Okay. Is that okay? T1 and T2, right? You can also try to ask the question, what's the meaning of this one? What's the meaning of this one? Then the idea will be the same, right? Whenever you're getting confused here, or you don't understand here, you go back to this canonical picture. You ask which operator does the job again. Ask the same idea as before. Which operator does the job in the canonical framework? Okay. Then you realize, okay, not surprisingly, right? You realize that, okay, I have to insert two operators, two find hat. But you have to really be precise that that two operators really inserted at the time slice T1 and T2. Okay, not something else, not somewhere else. Okay, you have to precisely insert the operator at the precise time slice. Because in the canonical picture, you slice your time. Many slices. Okay. This T1 and T2 tells you which slicing how to insert this operator. Okay, that's it. And this X1 and X2 accordingly tells you that for this insertion, for this T1 slicing insertion, you have to insert it at which space point. Okay, that's it. When you know this information, then it's not difficult, right? Just translate this to the two-point function. To the two-point function. Is that okay? Now, yeah, for those, yeah, maybe still, now, yeah, sometimes they're getting confused. What is it? Even mathematically, Suppose I know how to do this complicated sum. Now you tell me I have additional 2 field insertions, but what's the meaning? What's the meaning of calculate this whole object? Okay, even how to do it on my computer. Okay, do you know how to do it in your computer? To evaluate this path integral with these 2 insertions, right? So in other words, how can I understand that these 2 insertions? No, it's not trivial, right? In the calculation of this path integral, in the evaluation of this path integral. The point is you should understand it in this way. Fortunately, I have a picture here, okay? So that 2 insertion really mean what? It means, first of all, in this sum, you have many different phi configurations, right? That's something you do know, right? Now, suppose you discretize the space-time, or you treat this field theory as a spin system. Now you try to evaluate this path integral with these 2 phi. What are you doing? You are really doing something as follows. For each configuration, you get a number here, okay? Then you get a phase here, right? This is okay. You can put your computer, right? It's just a number. Now, what do you do for this one? Okay. For this one, what you need to do is just you have to pick up the value of this configuration at the particular space-time point. Okay. You take that value, okay, and you multiply with this phase factor. Is that okay? The point is, for each different phi configurations, this value could be different, right? Right? But no matter what it is, every time you perform this sum, you have to accordingly pick the corresponding phi value at this particular point. Is that okay? Then you multiply with this phase factor, and then you do the sum. Eventually, you realize that this 2 insertion does not trivial. It gives you something. Okay? It just affects the original average path integral without this insertion. It's different, okay? Right? It's clearly different, right? But with these insertions, every time when you sum over these phi configurations, you have to pick up the value, okay? You have to pick up the value at the specified space-time point. Take the number, okay? You take the number, you put there, okay? You take another number, you put there, and then you do the average. You can think about this complete sum with some kind of average, right? Average with this weight factor, okay? You sum them. Yeah, that's the mathematical way to understand how you perform this calculation with these 2 insertions. Now, physically, as promised, we know this has to be related with some 2-point functions. Okay? But now, which 2-point function? We have many 2-point functions. You know, we spend once a week, okay, a few hours to discuss all the different 2-point functions. Now the question here is which 2-point function we have to put on the right-hand side. Very good. So time ordered. Why?
Because when you insert the operator, you would put if t is bigger than t2, then the operator phi t1 would be on the left.
That's right. Very good. Okay. So this is another magic. Okay, it's very important. So according to this translation, back to this picture, right? If you agree that's the way to understand this kind of insertion, okay? If you accept that connection with this canonical picture, then automatically you realize that the earlier time has to be always located on the right, okay? The later time has to be always located on the left, right? Right? Almost by definition, right? Because you act those complicated state time sliced some state by some operator to get this one by definition, right? Early time is always on the left, on the right, and the late time is always on the left. So this guarantees the two-point function understanding of this kind of path integral is automatically time ordered. Okay? Always, right? Is that right? Suppose now the T2 is greater than T1, meaning T2 is later and T1 is earlier, okay? Right? Then this T1 has to be located on the right, right? Because that's the earlier time. And T2 has to be located on the left. It doesn't matter in this path integral you put this is left or this is right. This is no big deal. This is no difference, right? This is just functions. Okay? This is just functions. There's no ordering in the path integral. There's no operator in path integral. Right? Everything is functions, just the classic functions in the path integral, right? You can switch them as you want, but that's not important. The really important thing is you should distinguish which time is earlier, which time is later. Then you translate back to the operator language. The earlier operator has to be always on the right. So that's another magic. So like what we do for one-point function. So up to some prefactors, the prefactors could be different. Just you always use this n using the prefactor. This equals to a time ordered I hat x1, I hat x2. Okay. Okay, and you can have many alternative ways to justify why we pick up the time ordered on the right, not something else. Okay, for example, you can drop this time ordering. If you drop the time ordering, you get trouble. Okay, you realize that okay, that's not quite consistent. Make this equal to a two-point function without time ordering. Yeah, you can check yourself. Where is the problem? This means what? This means the impulse integral is much simpler to obtain this time ordered two-point function, right? Remember that previously, in order to obtain this time ordered two-point function, we spend a few hours, right? We use some control integral. We distinguish a lot of different two-point functions. Eventually, we get the time ordered, which is the Feynman operator, right? We really did a lot of work to achieve that. But this time it's just for free. It's just for free, okay? So you get the time ordered relation function for free. Now it's sad. Yeah, another note. Another note is the field insertion in the path integral. No meaning of operators. They are just the classic fields. or just the classic fields. Okay. So just classic field. I mean, as explained before, if you, for example, if you in statistics, you want to calculate these two field insertions, right? Even you put this phi is here, I mean, this phi is here, it doesn't matter, okay? Eventually, when you do the average, you will get the same result, right? Because in this average process, the thing you only care is you pick up some the field value for each configuration, okay? In the sum, you pick up the value, and this is the number. And you multiply these two number commute with numbers. You get the same result. So it's not an operator. The point is, this is not an operator. You shouldn't think, okay, in Parse integral, this is fine as some operator. No, that's not true. Okay? You have to switch your mind a little bit. Previously, we emphasized that from quantum mechanics to field theory, right, you have to change your mind to really think the field is operator. Now, drop it, okay? Now you should drop it. In Parse integral formulation, it's not. It's not an operator. Okay? Not an operator. So it shouldn't, then immediately you realize that this shouldn't equals to the two-point function without a time order, right? If you insist so, then it doesn't work. This is not equal to this one, right? Clearly, these two guys are not equal. Okay? These are not equal. Because this doesn't, for the left-hand side, if you switch these two, it doesn't matter. We learned it before. Right-hand side, if you switch two, it matters, okay? But this cannot be equal, okay? That's why we really need to put this time order T here. So it's not equal to this one, but it has to be equal to T order. Okay? T ordered, okay? So for bosonic field, we know for T ordered, if you switch these two, it doesn't matter. Okay, always time order by force. So this is correct. This is the correct relation. Yeah. So with this in mind, and immediately we promote the relation to the endpoint function. So one can define endpoint time ordered correlation function correlators by Parse integral. So what do I do? In general, even for interacting theory, okay, I want to construct the time ordered endpoint functions. Meaning I have the n operators too. Then, in terms of Parse integral, what should I write? From the above discussions, we know already we should include the n field insertions, okay? N field insertions inside the Parse integral. Okay? And then we normalize by the Parse integral without the field insertions. Okay? Without the field insertions. So why I choose to define the endpoint function using Parse integral in this way? You can immediately realize for example, this normalization, right? This normalization. So this normalization is convenient. It's consistent with the previous. It's consistent with the previous relation in the Hamiltonian or some other generalization or whatever. So in that approach, if you turn off this formula, if you turn off this phi, right? If you turn off this phi, if you drop this phi field, this phi is just identity. Then right hand side is equal to 1, right? You see? It's equal to 1. So normalized by this bare path integral is equivalent to say, if you don't have this phi, you just take the overlap between this vacuum and this vacuum, you get 1, okay? Okay? It's essentially because this normalization, right? Right? But that's just a normalization. It's not the most interesting thing is with this insertion. Right? With this insertion. So this is the natural construction of the endpoint function inside the Hausdorff. Okay. This is with normalization. Now, in the remaining time, today's lecture, we're going to stick to this definition and try to calculate this one, okay? In this path integral definition, okay? See whether we can get consistent result with what we already know before and what we don't know yet. Yeah, in particular, we should check the consistency with the no result. And we will realize this path integral calculation to the endpoint function is very convenient. So how to do it? So you have a definition, very good. Now how to compute? Right? Definition is not enough. You should know how to compute. How to compute this kind of using, for example, using this the new definition. Okay, this new definition. Now we use some trick in order to calculate this systematically. We develop some trick. This trick is the so-called generating function trick. So what do we mean by generating function? Generating function means in order to calculate this kind of object, we have to we first deform this action a little bit, okay? By introduce some source term. The source term coupled with the field phi. Now, once you deform this action, then because source coupled with phi, when you take the derivative with respect to the source, then it generates this phi insertion, right? It's very natural, right? Right? Because they couple together. You take the derivative for one, you generate the other. Okay? Right? That's the trick. So in order to introduce this trick, we first define some mathematical operation, which is called some new derivative, okay, which we denote as this delta G x. Okay, this derivative is respected to some is with respect to some function located at some space-time point. Okay, you see, I denote it as some kind of variation. It's indeed, it's a variation with respect to a function at a space-time point. So how to understand this one? For example, you can do the variation y with respect to jx. Okay. Okay. This means what? This means I fix everywhere y point except the x. Okay. Okay. I don't change it anywhere. This is a given function. Okay. J is a function. Okay. J is a function. I don't change it anywhere except for the x. Okay. Okay. And take the derivative with respect to jx. So this gives what? So this gives a third function. And then immediately we can express the jy equals to the integral jx times the third. Right? So this formula, we don't need any new tool. We know this is correct, right? This is the definition of third function, okay? Is that okay? Now I'm telling you, you can define a new derivative, okay? The new derivative, if I take the derivative for j, y, with respect to the jx, okay? Is amount to drop this integral, okay? But then you get a third function, that's it, okay? This is what we know before. From this, we can define a new derivative. Looks like this. Okay? Like this. Okay? Yeah, this should be okay. Now, you generalize this a little bit, immediately you realize another thing is true. Then, if I take this derivative with respect to a j, multiply with some arbitrary function, phi, for example, okay? So what if I do the derivative with respect to jx for such kind of integral? You guess the results? Right, of course, right? Because you can shift this inside, okay? Now, since this gives you a third function, right? So you have a third function left over inside, okay? Then all the j drops, but you have a third function remaining inside. Then third function kills this integral, but set this y goes to x, okay? So this will be equals to phi x. Now with this trick, with these tools, then it's enough. Right? We can go just straightforward. One. Go forward. For example, one can consider something called the generating function, which is the deformed action So how to consider the generating function? It goes like this. Okay. So record this is a generating function j. You introduce a source j, and it defines as a path integral with the action improved to include a j coupling term. Okay, right? So I make it this way. And I want to manifest this term, so I write this Lagrange density. Okay. So this is the action, entire action, previously entire action. Now I deform it a little bit by introduce a new term. New term is an integral j phi. Okay? Phi is a local field, and j is a local source. Coupled with this local source, j and phi, and then do the integral. I add this new term into the previous action, and then make this path integral, okay, together. So this is something called the generating function of, okay? Okay, this is something called generating function. So anyway, this is my definition. So if you walk from here, then immediately you realize if I take this j derivative and from a particular point, x1, okay? So let's do it. We already understand this new derivative, okay? Respect to the meaning of that. Now let's do it for this object, okay? So what do I get? So it's some kind of derivative, right? So let's shift it inside. So this is some exponential of some object, right? When you do the derivative of such kind of object, the first exponential does not change. So exponential remains, right? But you do have to do the derivative for this exponent, okay? For this exponent. So what is that? Of course, this does not depend on j. So okay, this does not change. So only contribution is from this one is the integral j phi. But we do know integral j phi, when you take this j derivative, you get just phi x. No, right? So here you get nothing but phi x1. This is the result. Okay, this is the result. But because of this, we know minus I 1 over z j equals to 0 delta z j delta j x1. But okay, this is almost, but it's not finished yet because now this path integral still has the j, right? Now, do the variation with respect to this j, you indeed get an insertion. Once insertion, phi x1, okay? Okay? See, that's what we want. But we don't want this piece. This still has a j phi coupling, so eventually we have to set j equals to 0, okay? See? The set j equals to 0, okay? The set j equals to 0. Now, in order to get it consistent with my correlation function definition here, remember that here in the definition we also have a normalization factor. We have to not only the insertion but also a normalization factor. So we have to divide by this normalization factor. So that's why we divide, take over to this z j equals to 0. Okay, this is the normalization factor. Then the point is, after all these steps, this is nothing but the correlation function, the 1-point function. also equals to this 1-point function. So as you can see, I employ this generating function trick by introducing this new source j. We successfully computed. Okay, we can compute this 1-point function here. Okay. Now this trick you can immediately generalize to endpoint function. With endpoint function. So even for endpoint functions, this is true, and this is the powerful trick to calculate for the path integral. So immediately you get this. This factor is because the quantum action is I. Okay, and this factor is because we need a lot more action. And apart from that, then the only thing you need to do is do the variation with respect to j n times. Each located at different position, okay? And eventually you set j equals 0, okay? Eventually you set j equals 0. Then you get the endpoint function. So importantly, this is also true as we denoted for interacting theory. You can see so far, even though we derived a path integral result, path integral formulation from the canonical picture, you see, and by performing some Gaussian integral, inserting, split the time and insert some complete phi or pi basis. In that derivation, indeed, we calculate for free theory because this is a Gaussian integral, right? It's easier. But the result should be taken to be universal, okay? The path integral formulation for a field theory is universal. It's true for both free theory and the interacting theory, okay? So if you accept that, then all this kind of result is valid also for interacting theory. It doesn't matter if you are dealing with free or interacting theory. Is that clear? Now, it's still a little bit abstract, okay? It's a little bit abstract, even though we get this formula, but still, we don't know how to reproduce the endpoint function result for given specified free theory or interacting theory, right? Still some abstract formula. Now, let's come down to the earth. So, to try to calculate this more explicitly, to calculate from the left-hand side. So the point is, in free theory, everything is clear, and so this Zj can be computed explicitly. And compute the explicit. So how to do it? Then you may have realized that in free theory, what do I do? What should I do? In free theory means this Lagrangian density is the quadratic form of this phi. Okay, it's a quadratic form of this phi. Now the only new thing, you have a new coupling j phi, but still is a quadratic. So the integral over this phi is the Gaussian integral. Okay. So you can do this Gaussian integral explicit. So that's why free theory you can make everything explicit. Yes. Okay. So we get the result. So what is the result? The result is, now let's put index 0 denoted free zero. Like what we did before. Because later we're going to the interacting series. That's distinguished. So for free theory, C0j equals to, after calculation, you get this result. You get this result, okay? Then you ask me, yeah, of course I jumped a little bit. There's a few seconds calculations to get this one, okay? To get this result. Importantly, there's a df appears here, okay? df appears here. Then you ask me, how do you know this is the Feynman propagator? It's not some other propagator. Again, that comes to the question, right? We have many propagators as green functions, right? We have 4, right? We have Feynman propagator, we have advanced, we have retarded, and we have df tutor, okay? We have different types of green functions. And how do you know one should put the Feynman propagator here? Okay. This is related to the previous time ordering lecture in the past integral. Okay. Okay. First of all, for consistency, this has to be df, right? Because if you use this, if you take use of this j, okay, if you do twice variation with respect to j, and then set j equals to 0, you should be able to get a 2-point function, right? You do twice, you get a 2-point function, right? And we know this time-ordered 2-point function is precisely the path integral with 2 field insertions, right? So time order has to be there, right? So in order to produce that to that time order, here it has to be df, no? Because if you do variation with respect to j twice, then you pick up df, right? So df is precisely the time order, the 2-point function. So for consistency, this has to be df. Okay. If you want to ask where this df comes from, or where this Feynman property comes from more deeply from this path integral, right? It's an interesting question. I suggest you think about it. Why this has to be df, not something else? Okay. Yeah, it's related to this time order nature in path integral. In the path integral. But at this moment, we can take this for consistency. It has to be, okay? Not some other problem. So, with this expression, we can work out the higher point correlation functions, okay? We can take use of this result and try to calculate some others. See how much time. We have half an hour. I think that's enough to proceed the calculation. Yeah, let's do it. Do it. Yeah, let's start from this Z0j result. Try to calculate the higher point correlation functions, but still in the free theory, and then go to the interacting theory. Then we can finish, okay, this course. So go to higher point, for example, 4 points. Okay. 4-point functions, okay? 4-point functions. So in order to calculate the 4-point functions, namely, because this is the free series, I use this vacuum. Namely, the time-ordered phi operator 0 to delete this down free fields. Something like this. X2, 3, X4. Okay. We want to calculate this one. Okay. Now we already justified that this equals to, this has to be equal to minus I to the fourth 1 over Z0, 0, and equal to 4 times the 0 J. Okay. That's my Z0 J already there. Okay. We know what is Z0 J, and Jx 1, Jx 4. Okay. Eventually set J equals 0. Right. So this is the path integral formula for this curling for the 4-point function. Okay. Now the point is, I know what is this guy. I know how to do this variation or derivative. Then I can just go straight forward to say from the right-hand side formula what can I get? Okay. What can I get? Yeah, let's do it. Then immediately you realize that, yeah, it's nothing but, it's not a big deal, right? It's nothing but the calculation somewhere we already implement, carry it over, yeah, because we know how to do it. For example, we can, to proceed, let's again using this shorthand notation. Otherwise, the formula will go to the shorthand notation. So in the shorthand notation, this will be equals to here I also escaped some prefactors. Let's don't worry about some prefactors. Okay, some prefactors. And using some shorthand notation, this will be equal to half. This will be equal to the exponential minus half Jx d xy in jy, and then set j equals to 0. See, the repeated index means integrated over. Okay, the dxy means the Feynman propagator from x to y. Okay, from x to y. You see, it's the same shorthand notation as we introduced before in the Schwinger-Dyson. Okay. Then it becomes more clear. Now, this has to be equal to, let's first take this variation with respect to the J4, okay? J4. So what is that? Then leftover thing is just the J1 to J3. And do the J4, what we get is you see, let's do one by one. First, you do the variation with respect to J, you get a minus half. Then you get delta function for x, right? By definition, right? You get the delta function for x. And then the delta function for x will set this x to 4, right? So what you get is half minus half d4y jy, okay? And you get another term, right? Because you can take the derivative with respect to jy, okay? Get another term. The other term is the minus half jx dx4. Okay? So this is the derivative with respect to the J4. Variation with respect to the J4. You work once, you get this result. Don't forget, you still have the exponential. This is the exponential minus half jx dxy jy. Okay? And this is the last step, okay? This formula should be understood as this bracket and this exponential is the whole thing, okay? And this derivative, this kind of derivative is the operation act on this whole thing. So after all this action finished, in the last step, you set j equals to 0. Okay, this formula means. Then you just work it out straightforwardly, right? Just work it out straightforwardly. The important thing is you notice that these two terms are not independent. These two terms are actually equal, right? Because this is just a repeated index, okay, y. It's integrated over. You can change this y to x. Then you realize that this is the same thing, okay? This is the same thing. So, yeah, so you go, you just go to continue to calculate this one. For example, this is equals to minus jz, and switch to z instead of x and y. And e, j, and then j equals 0. Okay? And then you take the derivative with respect to the j3. The j3. So what do you get? Yeah, you basically do one by one. Do the derivative one by one. Okay? It's not difficult. It's super easy. You do the derivative one by one. So what do you get now? You get J1, J2. Now let's do it, okay? Let's do this J3. Now for this term, first of all, act on this term, okay? For this term, we get a delta function 3z, okay? Delta function 3z, you will set this z to 3. So I will get a minus d34, okay? So minus d34. And, but there should be also terms if you act this derivative with respect to J3 on this later part, okay? There are two, in particular there are two. But from this step, we already understood this symmetry, okay? These two will just amount to pick up a minus JD term. That's it. Okay. So here we'll get the J, D, D4D, JW, D3W. Right? Right? But when you act on this later part, you shouldn't forget this is earlier. Okay. So this JD put together. Okay. And then there's an explanation following term. J, D, J. And eventually you set J equals 0. Okay? This is this term. Now you go continually play this game. You continue to play this game. Now we are here for the J2. Now for the J2, you have the 3, 4, JD, EZ2, plus D23, JD, EZ4, plus JW, DW3, D24, minus JW, DW3, JT, DZ4, JR, DR2. Yeah, we have too many terms, so half JDJ, eventually J equals 0. Okay? And yeah, we're almost done. The last step, we just obtain the D34, D12 plus D23, D14, D13, D24. Okay. So this is precisely the result we derived by other means. Okay. So we reproduced successfully the previous result for 4-point function, because this is nothing but the different contraction for these 4-point functions. Okay, these sums. These 3 terms. Okay. Okay. See. For the 4-point, these are the 3 terms. These are the 3 terms. Now, what about the interaction? Okay. It seems it's more interesting. It's more interesting. So let's push. Oh, yeah. Let's push this to the interaction. So far, we're only doing the free case, right? So as you can see, for that purpose, to calculate in free series, this Z0J is enough, right? Really, this function is enough, right? This generating function is enough, right? Because this is the compact generating function for free series, right? It's a quadratic in terms of J. See, but the point is by this, if you have this in your hand, okay, you can generate all the free higher point correlation functions. Okay. Okay. Is that okay? I mean, physically, you can understand this one as what? So J is a source. Again, physically, this means when I have a source J, then through this Feynman propagator, okay, overlap with another source, okay. Okay. This generating function in free series amount to measure this process from one source and then propagate and then to the other source. And, what are the amplitudes? Okay, what are the amplitudes? So this is the meaning of this generating function. What are the amplitudes? Because without this J, the partition function has the meaning of amplitudes. Okay. Now with J, you just improve the previous amplitudes by including this new source. Okay. That will be the understanding. So, but the problem is that we're more interested in to go into the interacting case. Again, let's specify a little bit. Otherwise, everything is too abstract. Let's specify to the qubit theory with this coupling G over 3 factorial. Okay, it's precisely the same theory we analyzed before by other methods. Okay, now we want to use this completely new tools to calculate this one. Okay. So, and the first thing always we have to ask, what is the Zj? Okay, what is Zj? What is the generating function for this interacting theory? So that should be e phi e to the I integral. This Lagrangian, right? Plus the source term, okay? Because we want to improve the action. Then plus the coupling term or interaction term, okay? This is what we have to do, have to deal with. This is the path integral. You see, this path integral is a little complicated, right? You see, this is the path integral. This is the free part, but now we have a complicated coupling, phi qubit interaction. Okay. Okay. And if you want to use this generating function trick, you have to introduce another J phi coupling. Okay. So I write here very simply, abstractly, but you should understand that all these J phi are local functions. Okay. They couple together, and eventually they have to integrate, take the integral over x. Okay. Okay. So this is Jx phi x. This is the phi x. There's a 3 phi x. Okay. and then integrate over. And this as a weight factor for this entire path integral. Yeah, that's what it is. Now it's always, we can do the trick, okay? We can do the trick. We can assume this coupling is small, okay? We can do the perturbation. We can do the perturbative expansion. The perturbative expansion assumes this coupling is small. This G is very small. If this is small, we can expand, okay? We can do the Tanner expansion for this exponential with this small coupling term, okay? Only for that term, okay? Because this previous term we can factorize out. So then this will become E phi E I integral now big bracket. Now we do perturbative expansion, right? The first term is 1, okay? The first term is 1, leading term. Now the second term is ij over 3 factorial ez integral phi d will be, right? Right? You just do the Taylor expansion for this term. Okay. So this is the second term. What about the third? The third term is ig over 3 factorial square. Okay? Okay? And half dz double integral dw and phi 3c and phi 3. Okay? Of course, you have some higher terms, but let's don't discuss those higher terms. We always stop at some order in the perturbative expansion. Right? This is what you have. Now the only thing, now the problem becomes how to calculate the term by term. You see? Term by term. Term by term. So what is this? Let's look at this. So if you want to calculate the first term, what it is, this is what we already know, right? This is the free result. This is the free result, right? But what about this second term? The second term is, see, we have 3 new insertions. We have 3 insertions, phi, right? Phi, but all at the same point, okay? In the path integral, okay? We have to calculate that one. And for this one, we have how many insertions? We have, we have 6, right? At 2 different points, okay? This is only the J, this is only the Zj, okay? We haven't taken the derivative with respect to J. In order to read off the correlation function, we have to do the variation with respect to J. You see, right? So that variation will pick up some more phi insertions, right? Right? That's what we really want to calculate. Okay? But conceptually, this means what? If we want to particularly calculate the correlation function for interacting theory, for example, 2 points function, then the problem evolves to calculate the higher point function. You see? So some lower point function in interacting theory becomes higher point function in free theory. You see? Because after this expansion, this corner becomes free, right? You can alternatively understand this is a structure for some higher correlation functions in the free theory. Okay? Because now you expanded this interacting theorem out. Okay? Expanded this interacting part out. So it becomes the correlation function. Everything becomes a correlation function. Free theory. Okay? So this is the idea. You turn to interacting problem to a free problem. But now the payment is you have to go to higher. You have to go higher. Okay. So then let's do it. Let's do it. So here we did for free theory already. Now let's do for the interacting theory. let's employ the formula, but as claimed, this formula is valid also for all. Let's now try to calculate the interacting two-point functions. Okay, two-point functions. And for following the definition, this is, you see, now I don't use Z0 because it's the interacting theory. But I do put 0 here because source now is trivial for the normalization factor. Okay? So you take twice derivative with respect to J for your interacting generating function. This is enough to produce the 2-point. This is enough to produce the 2-point correlator for the interacting theory. Okay? Now you plug in this star formula. Let's call it, this formula is important. Let's call this formula is a star formula. Okay? This is a star formula. Also, you should plug in the star into here. Okay? Because here we have to deal with the interacting generating function as a function of J. So you plug in the star here. The star has to be put here. Okay. Then you compute order by order, one by one. Okay. So let's see what happens for one by one. So as claimed for the first term, what do we get? For the first term, after everything is finished, or J, eventually J is set to 0, what we should get? We should get Z0 over Z0 times df. No? We should get this one. It's free, right? You see? This is the first term. These factors come from here by definition, right? And these factors come from that free part path integral, okay? And then with df, okay? As you can check. No? Now what happened for the second? Now the second one, now this factor will be the same. So let me don't. Yeah, this is overall numerical factor will be the same. Just don't bother with those. And for the second one, you will get this 1g over 3 factorial dz. Now, as emphasized, now everything becomes correlator in the free theory after the perturbative expansion. Okay. So for the second, what you have is this one. Right? Is a time ordered 1, 2, 5, right? Is a time ordered 5-point functions for the free theory, but 3 of them located at the same point, right? Okay? But no matter the position, which kind of position, we know by following Wick's theorem, if the insertion is 5 points, if it's in the free theory, what is the result? 0, right? Wick's theorem says that in free theory, all the higher correlators have to be contracted pairwise. Okay, you have to pair them. If you can successfully pair them, then you get non-trivial result. If you cannot, then it's 0. Because we cannot pairwise the 5 points. They're always one single out. So, theory. So this has to be 0. Okay, because you have 5 points. Okay, not all the number. It's not an even number. Okay? So this is given by the Wick's theorem. Now the last job is the last term. Okay, last term looks a little complicated indeed, which is the ij squared 3 factorial square and half dz dw t phi x1 phi x2 phi phi z, 3 point at phi z, and 3 point at phi w. Okay. So how many points? Look, this is a free theory time ordered higher correlators. How many points? 1, 2, 5, 8. Okay. So this is the 8-point function. But don't be scared. I mean, it's free theory. Okay. Doesn't matter. It's 100 points, or just put it on a computer, for example, to tell you the result. Okay. So this is the 8-point. 8-point function in free theory now becomes a counting problem. You just count how many different contractions according to Wicke's theorem. Okay, just count it. It just give you a correction factor. That's it. So let's do the counting. Let's do the counting. Let's do the counting. Then, yeah, you can count it by yourself. For example, let's write this more explicitly. Yeah, these are the 8 operators. Okay, these are 8 operators. You just try to contract them, right? Pairwise, according to the theorem, just pairwise. How many ways to pairwise them? Then you get the result. Right? For each pair, you get a Feynman propagator. That's it. Okay. What do you get? So you get D12. D12 means from x1 to x2. DZZ, DZW, DWW. So this kind of contraction, how many times? How many times? Counted.
9.
3 by 3, right? This is 3 by 3. So you have a line, right? You have a line. So let's search for some other contraction. For example, 1, 2, and Z2W, but 3 times. How many contractions for this? See, we don't have time. Let's give the result. So you have 6. Okay. Now you actually have many. This is a very interesting counting problem. Okay. So for this one, you get 18, okay? So there are a few more. For this, you get line, okay? And you have 3, yeah, you have 3 more. You have points, you have, yeah. Just wait. D, Z, D2W, DZW plus U18, okay? Plus D1W, D2W, DZW, DZZ. You have 18, okay? And plus D1W, D2Z, DZZ, DWW. You line plus D1W, E2Z, EZW squared, you have 18. That's it. Okay. It's a little complicated, but it's, it's a middle school problem. Okay, just count it. Count it. That's it. And you also notice that among these, they are not quite independent. There are some terms. For example, the 3rd one and the 6th one, this one, yeah, this and this are the same, okay? Right? You can see it? Just different parameterization, right? They're the same. So, and the 4th, and this one, and the 7th, and this one, okay? They're the same. You see? You see? Just parameterize, different parameterization, W and Z, right? And similarly, this one and this one are also the same. So you can simplify this one, okay? So eventually you get the result. You get the result with some bracket, and first term is d12, and the second term is 0, and the third term is the contributor with if some of the terms degenerate, eventually you get only 5 independent terms. Okay, you get only 5 independent terms. 5 independent terms is 1/8, 1d2, dz, dzw, dww, plus 1/12, d12, dcw cubed, plus half d1z, d2z, dzw, dww, plus quarter d1z, dzz, dww, dw2, plus half d1z, dzw square, dw2. Okay, that's it. Yeah, this is the result. Now, if you don't like algebraic, you like a picture, you can draw it. Okay, you draw the picture. I have 5 terms. You learn how to draw the graph, right? For example, you learn how to draw the Feynman graphs. You can turn this to the graphs. So immediately you realize that these three terms, you reproduce the previous Feynman rule result. Okay, you realize that's it. That's the same thing. Okay. The only now some new pattern is then we should be honest, right? We're scientists. So when you realize that then 2 new terms, these 2 new terms, it seems these are new, right? These are new. Then you ask what happened. So it seems I didn't really get a consistent result with what was before. As I said, these 3 terms are precisely the same as the result we derived from other approach. But what about for these 2 new terms? The magic is hidden in this bracket. Okay? This bracket. So this bracket is highly non-trivial. Why? Because this bracket is this one. Okay? Okay? It's a normalization factor. So what is this? Think about it. This is the free path integral without source. This is the interacting path integral without source. So you can think about this is the z over z0, right? So this is precisely the normalized time-ordered interacting term, okay? Okay? So that term is all, in free theory point of view, is also included in the many Feynman graphs, okay? That's the point. And that Feynman graph is in the denominator precisely cancel this blue line. Okay? This happens in very precise way. It's not some cheating argument. Okay? It's just mathematically cancelled, magical, okay? Term by term. Okay? Then indeed, the claim now, indeed, the final result is only these 3 terms. Okay, in this order, in this g squared order. Okay. And then it indeed reproduce the previous result. But there's some interesting cancellation here. This blue line cancels with this bracket. This bracket. The bracket is this one. Okay. And this one is let me just wait. 1 second to. So this bracket or this one is nothing but the free correlator for this time ordered interacting. This one, right? You see? This is very, very interesting. This means in path integral language, different framework connected very laterally, okay? Okay? Very laterally. For example, this happens in this case. Just this factor, you can interpret it in this way. Okay? It's interpreted in this way by definition. Okay? The point is, you can think about this. This is the interacting term. You can think about it in another way. Okay? You can think about this term is some new insertion. Yeah, this piece is some new insertion. Okay? Okay? This is some new insertion. This insertion is inserted in the free theory. Okay? That's why I write a time order exponential this interacting term. You see? Right? Because that's indeed the insertion. Every insertion should be in the operator language should be understood as time ordered already, right? So this is a bunch of many different correlators inside because this is exponential. Okay. Now whatever it is eventually time ordered. So that's what I mean. This factor, which is contributed here, also include many graphs. Okay, and that graph precisely cancelled with these blue lines. Okay, so only the red line left over, which is precisely consistent with the previous Schwinger-Dyson result. Yeah. So, okay, let's stop.
这里这个东西它的倒数是否就等于这里加的符号？